another object in simple harmonic motion with the motion detector here. So what we're going to do is grab this cart, we're going to pull it back here to an amplitude of where x equals -a, standing for the amplitude, and whoom, let it go. It's going to zoom back, and imagine right when it gets here to x equals 0, then we start the motion detector here and start picking up this graph right here. So there's a couple of questions on here that they get to. How can you get all this information off of there? So what they want you to do is on this part, they say they want you to, knowing that the inner system has 10 joules of total energy, calculate the values of mass, spring constant, and amplitude here. And so expressed in words and equations. I'm going to write focus on the equations and just say the words here. So the first thing that we can see here, I'm going to write as this. Well, they told us the total mechanical energy equals 10 joules, right? But at a certain point on this oscillating system, that will all be from the kinetic energy. And so we can set that up and say, all right, well, 10 joules of kinetic energy is equal to 1/2 times the mass times the velocity squared. Well, we have two unknowns, the mass and the velocity. But if we look back at this graph, we can see that our maximum velocity is 2. So we can plug that into the equation. And we can say that 10 joules is equal to 1/2 times mass times 2 squared. And if you do that, I'll just write it right here off to the side, we'll get the mass is 5 kilograms. So once you do the algebra there. So now we have the mass. Now where do you go? The natural inclination is like, well, if it's 10 joules of kinetic energy, then at some point here it's got to be 10 joules of potential. So you start running around with the potential energy. Sorry, I was getting ready to write it like that. Let me write it the way they normally do. So the potential energy of the spring is 1/2 kx squared, but we don't know k, and we don't know how far back we pulled it. So you reach a dead end. The way to go here now is the period. The period of a spring is 2 pi square root of the mass over the spring constant. Because we know the mass now, we don't know the spring constant, but we can actually get the period off of the graph there. So if we look on this graph here again, it starts here at 0 seconds, and by the time we get here to 4 seconds, we've completed a cycle. And so we do know the period. So we plug that in. 4 seconds is equal to 2 pi square root of 5 kilograms over k. Do your algebra, solve for k, and you'll get about 12.5 newtons per meter. Not exactly, but let's round it off. So now we've got the spring constant. So now we can use our energy system here. So we can say the elastic potential energy is 1/2 kx squared, but I'm going to call x a because that's the maximum amplitude. That's when all the energy is spring energy. So we can set it up. 10 joules is our maximum energy. We solved our spring constant from here, so that is 12.5 newtons per meter, and we can solve for a. And if you do the algebra there, you'll get that the amplitude's roughly 1.26 meters if you round it off there. So that is how you solve those. And they could have easily given these in a different order and told you something about the mass, and then you find the total energy. They love to mess around with that. So the next part here is they say that we have a dart shot to the right at the cart at a moment when the cart's momentum has a greater magnitude than the dart's momentum. Meaning that either the cart's more massive or is going faster. In case 1, the dart is shot into the cart at a time t equals 12 seconds, and in case 2, the experiment is repeated exactly as before, but the dot is shot into the cart at a time t equals 14 seconds. The dart embeds itself into the cart, so it's an inelastic collision in both cases. The graphs below show the velocity of the cart as a function time for both cases from 20 seconds to 35 seconds. The dotted graph shows what the plot would be had the dart never hit, basically. So explain these two graphs here. Well, let's look at case 1. They said it happened at 12 seconds. So it's kind of confusing. You got to come back here and you got to look right here at 12 seconds. The cart had its maximum positive velocity, meaning it was going this direction, wherever it was, whether it was at its maximum positive velocity. Actually, it means it was going right this way, and we shoot a dart into it right at that time. So So the dart goes in there, as it's already moving that way, it is going to cause it to speed up, right? It's going to hit there and the way it was already moving, so it's going to speed up. And so if we look here, remember the dash line is what it was doing, so boom, we get a little bit of boost in speed. That makes sense. So, and then the other thing you got to look at is look what happened to the period. So the period before was from here to here. And you can see that the period now is just a teensy bit longer. So that makes sense, just a little bit here. And the reason that that makes sense is that the period of a mass on a spring is proportional to the square root of the mass. So more mass should mean a longer period to repeat the cycle there. What about case 2? They say it hit at 14 seconds. So let's look here. At 14 seconds, you can see that we are at our maximum negative velocity right there. So we weren't traveling that way. Let me use a different colored marker to indicate it. We were going this way at our maximum speed. And then boom, the dart comes in and hits just like before, but we're going that way. So it's going to push the cart back a little bit. It's going to slow it down a little bit. And that's what we see right here on this graph. So you can see here, again, the dotted line is what it would have been. And so the solid line, we've lost some speed here. But just like the case before, our period here is just a teensy bit longer. And so that makes sense because we've gained mass and it should take a longer time to complete a cycle.